Thank you for introducing everyone. I'm Taro Abe. Today, I want to talk about the dynamics model of Excavator in the open source physical simulator for developing autonomous construction. Now start.
More stable and that you can get a much
First, I want to talk about the background of our research. We are developing an open source platform for autonomous construction called Opera. Opera consists both a real machine and its physical simulator with Unity. Opera provides the ROS2 interface for
I have a follow-up question. Thank you.
Simulator and real machine.
Do you think you can expand the application of your methodology, not just on roof inspection?
And then deploying them in the field. However, to be useful, the simulator must be carved like a real machine. Matching mass value is not enough. We also need to capture dynamics effects such as actual dead time and the hydraulic responses. But the current status of the simulation is that dead time is not.
Okay, thank you.
And my dynamic behavior is not fully simulated. So the object of research is to simulate the actual behavior of hydraulic simulator. We apply a parameter optimization method to the dynamics model constructed using only manufacturer specification and simple measurement, thereby minimizing the differences between the simulation and the real machine behavior. And we focus on minimizing the error in joint angle trajectory during typical motions. The optimization proceeds in 3 steps. First, implement dead time functions that delay command, so just a real excavator. Second, minimization difference in joint angle response between the actual and the simulator. And third, minimization of the convergence time in response to input between the real machine and the simulator. Now, I will talk.
The next presentation is entitled Sensor Fusion.
The actual hydraulic excavator have a dead time from input signal through hydraulic system to joint motion. By applying a dead time function to delay the input by the same time, the simulation can reproduce the delay behavior as the actual machine. And then, next, we adjust some parameter for minimization of the difference in joint angle response between the actual and the simulator. So here is the formula for controlling the torque for each joint about simulation. And we can change the behavior joint moving as a cold stiffness and damping parameters. You can show this formula. For every parameter pair, we selected a pattern that minimizes the mean squared error between the joint angle value response of the real machine and the simulator. And for example, about the joint, this table, so you can show the right table, shows that we can select this parameters pair as they show a rectangle, rectangle. So next, then, while keeping a stiffness fixed, the damping is fine-tuning to minimize the difference in convergence time to the input. By reducing the difference in response time between the real machine and the simulator. For example, in case of arm joint, we can select the damping param value as we show a rectangular one. So, like the right table, we can show that. So we choose the rectangular one. Finally, we can get a parameter for simulating a dynamic behavior. Here are the result of our parameters optimization. We tune the stiffness and damping for each joint, and swing, and boom, and arm and bucket. This slide shows the arm joint result. On the left, you can see the moving pattern for optimizations. The arm moving is up to then down, so repeating the movings. On the right, you can see the difference between the real machines and the simulator after optimization. The horizontal axis is this time, and the vertical axis is the joint angle. This graph shows that the simulation replicated the real machine's behavior with setting level. Then, to evaluate the model and the multi-joint loads, we executed the digging motion and approaching, approaching and digging and rate. You can see the actual machine simulator response differences. The horizontal axis time and the vertical axis the joint angle. Across the entire 24-second motion, the average root mean square error per joint was lower value, which means that the simulation replicates the behavior of the actual machines. And finally, I want to conclude my presentation. We confirmed that the dynamic model of the hydraulic excavator, constructed using only manufacturer specification, and the simple measurement results can simulate the behavior of the real machine through a parameter optimization that minimizes behavior, differences the physical simulator. The excavator simulation is available this URL, GitHub repository, as a GitHub repository. Finally, here is a principal reference that informed our methodologies. Thank you for your attention.